Hello and welcome to this video for Chem 20. In this video, we are going to look at the sharing of electrons in a molecule and whether or not the sharing of electrons is equal or unequal. So essentially, your nucleus, if you remember, is a positive charge because inside the nucleus is where the protons exist and the neutrons. The neutrons don't have a charge, but the protons are positive. So the nucleus is positively charged, and it is pulling on the electrons that are orbiting around in the energy levels. It's pulling on them because they're negatively charged and they have opposite charges. Okay, and so essentially what's happening when two atoms are trying to share electrons is the nucleuses are having a tug of war between those two electrons that they're sharing, or potentially the 4 or 6 that they're sharing, depending on if it's a single, double, or triple bond. So the question is, will they share them equally, or will they even share them at all? As we know, in an ionic compound, they don't even share them at all. The metal completely takes it away, the non-metal completely takes it away from the metal. So why does that happen? And how can we predict when this happens? And so the topic that we use to understand this is called electronegativity. For short, we write EN for electronegativity. So the electronegativity of an element is its relative measure of its ability to attract the electrons in a chemical bond. So as I said, there is an attraction between the nucleus, or specifically the protons of the atom, and the valence electrons in the adjacent atom where it's trying to share electrons with. And again, this attraction is just because the protons are positive and the electrons are negative, and so they have opposite charges, they attract each other. Now, there's actually a number assigned with an element to show how strong its nucleus is at attracting another atom's valence electrons. So how strong is it at pulling a pair of shared electrons from another atom? How strong is it pulling on that? And that number is written right above the element symbol on your periodic table. The numbers range, I believe, from 0.7 to 4.0, I believe, is the trend in the periodic table. Okay, so iron, for example, is 1.8. The higher the electronegativity means the greater the attraction is, the stronger the nucleus is at pulling on the electrons. Another word for wanting electrons is affinity, electron affinity. It wants them more. So there is a trend on the periodic table. If you look on the periodic table, at the very bottom left of the periodic table is francium, which is 0.7. That is the lowest electronegativity on the table. And the top of the periodic table on the right-hand side, we exclude the noble gases. So the noble gases, because they're not involved in bonding, so this is the value, again, of how strong it attracts bonding electrons. And again, noble gases are not involved in bonding because they're already stable. So if we ignore the noble gases, on the top right corner then is fluorine. And fluorine has the highest electronegativity of 4.0. So understanding this electronegativity has helped us to understand, again, whether the bonding will be ionic or molecular. And there's actually, within molecular, some subcategories that we're going to talk about. We're going to talk about bonds, whether or not they're polar covalent or nonpolar covalent. So this is just an image, again, to show you this trend in the periodic table, how, again, the bottom left corner is actually missing the francium level there, but francium would be even lower than cesium, or it's the same. Let me just grab my periodic table. Francium is 0.7. Actually, cesium is 0.8. This chart's a little off, and francium is 0.7. So francium is the lowest, and fluorine is the highest. And so the trend is, as you go down, it decreases. As you go to the right, it increases. So again, fluorine is our highest, top right. Bottom left, francium is the lowest. So we're going to talk about this trend and why this happens. So as you're moving from left to right across the period, the electronegativity is increasing. The atomic number is also increasing, right? When I go from, let's say, boron to carbon, I'm going from atomic number 5 to atomic number 6, and then to nitrogen, atomic number 7, and so on. Every element you go over from left to right increases by an atomic number of 1. However, when scientists have studied the size of atoms, they've noticed that as you follow this trend, the size of the atom actually decreases, even though electronegativity is getting bigger and the atomic number is getting bigger. Why does the size decrease? So here's an image showing again, as we're going across the periodic table, these are the electron clouds. The electron clouds are getting smaller and smaller and smaller as you go from left to right. As you jump down from one period to the next, they get a lot bigger. But when you're within one period, going from left to right, they're decreasing, decreasing, decreasing. So here's why the size decreases as you're going across a period. Because the size of the atom depends on the radius of the energy level containing the valence electrons. So again, the volume or size that an atom makes up is based on the electron clouds around it. And the biggest or the furthest electron cloud is the valence electron cloud. So in any given period, the valence electrons are the same energy level, right? Because when you're in a period like period 2, they all have 2 energy levels. Their valence level is the second energy level for all of them. So as you move across the period, you are adding more protons and 1 more electron, but that 1 more electron is going into the same valence level. If it's, again, period 2, the second energy level. Okay, so as you're adding more protons also, that's more positive charge. So because there's now more positive charge in the nucleus, it can actually pull the valence level in closer to it. So the valence level actually gets pulled in, and that makes that electron cloud that makes up the volume of the atom become smaller and smaller and smaller as you're adding more protons, as long as the electrons are in the same valence level, which is what happens when they're in the same period. So here again are some period 2 elements. So let's say we have lithium. Lithium has 2 electrons in its first energy level and 1 electron in its second energy level. Okay, but again, notice I'm really bad at drawing circles here. Let's just draw a semicircle to represent that. So 2 electrons in the first energy level, 1 in the second. So its valence level is the second energy level. It has 3 protons pulling on that level. But when I move over to carbon, carbon now has 6 protons. It still has 2 electrons in the inner level, and now it has a total of 4 electrons in the valence level, but the valence level is still the second energy level, right? This is the first energy level. That was the second energy level. Okay, so it's still the same energy level. So adding a couple of electrons in there doesn't actually change the size, because remember, electrons, we say, don't have a size. They don't have a mass, right? However, they do make up the volume of the atom. But now that I have more protons in the nucleus, those protons can pull the valence level in closer to it. And so that's why the size gets smaller and smaller and smaller as you go across in the same period. Because again, you have the same energy level and the second energy level as your valence level. So you're not adding any valence levels. Once you skip down to the next period, you do add another valence level. But as long as we're in the same period, we're at the same valence level, but we're getting more and more and more and more positively charged particles in the nucleus, so they can really start to attract the valence level, the second valence level in this example, and pull it in closer and closer and closer. Okay, so this is why size decreases when we're in the same period as we go across from left to right. So then the next question is, though, if the size decreases, why is electronegativity increasing? Why is there this opposite relationship? And it has to do with the strength of attraction, which depends on 2 factors. Okay, the distance between the protons and the electrons, which actually plays a really big role on the attraction. So if this is my proton and this is my electron, if my distance, let's say one distance is a half the other, the relationship of attraction changes with the square of the distance. So it's actually changing by a factor of a quarter rather than a half. Okay, so in other words, the further away they are, there's actually starts to become a really big change in that amount of attraction. So that's why when it's smaller, the atom is smaller, the valence level is closer to the nucleus. So that distance being closer enables it to pull on those valence electrons more. And again, electronegativity is how strong it can pull on the valence electrons of another atom. The number of protons are also affecting it, and that's why we said as the more protons you add, the stronger that force becomes. But it only has a direct proportional relationship. So if you double the protons, you double the attraction. Whereas the distance, like I said, changed by the square of the distance. So distance plays a bigger role. But if you are asked anyway, for the two factors that affect electronegativity, it's the distance between the protons and the electrons and the magnitude of the protons, or in other words, the number of protons. The more protons, the more positive charge you have to pull on the electrons. Okay, so that means an atom that is small and has a fair amount of protons compared to other atoms in its same period, like fluorine, will actually have a very large electrostatic attraction. We've used that word before, but remember it means an attraction between positive and negative charge. So a small atom like fluorine will have a large attraction and therefore a high electronegativity. Whereas big atoms may have lots of protons. If you look at francium, for example, it has 87 protons. That's huge. However, there's so many electrons that, like, there's so many energy levels, right? If I were to draw francium, so francium has 87 protons in its nucleus, but it's in period 7. So it has, is it 7? 1, 2, 3, 4, 5, yeah, period 7. So it has 7 periods of electrons. So 7 energy levels. So we've never even drawn them that big, but this is how big it would be. I have 1, 2, 3, 4, 5, 6, and in its 7th energy level, it has its 1 valence electron. So for the nucleus to be able to pull on the valence electrons, which are again the ones we're talking about for electronegativity, it has a really far distance. And there's a lot of shielding, they say, by the inner levels of electrons. Okay? So when you have lots of protons, the caveat there is that they usually have a lot of electrons, a lot of inner levels of electrons, a lot of orbitals. So it's too far for the nucleus to attract the valence electrons that it's trying to share with another atom. So the electronegativity is actually small. Okay, so now based on the electronegativities, what types of bonds can we have? So we've talked about ionic bonds already, and we know that in an ionic bond, there is no sharing of electrons. There's a complete transfer from metal to nonmetal. Why does this happen? It's because of the electronegativity difference between them. Metals have a very low electronegativity, so they are attracting electrons, but not nearly as strong as the nonmetals. The nonmetals have a very high electronegativity. So because their electronegativities are so different, the difference between them is so large, what happens is the nonmetal will completely rip the electrons away from the metal. And then we will form our positive metal ion, our cation, and our negative anion for the nonmetal. And then because the ions are oppositely charged, they will just attract to each other like magnets, and that forms the chemical bond that we call an ionic bond. So in an ionic bond, the metal completely loses, well, I'll draw the electron as a dot, but the metal completely loses it and gives it to the nonmetal. And then the nonmetal becomes negative, the metal becomes positive, and then they get attracted by their opposite charges, like magnets. Okay? And this is again happening because our metal is usually very low. It could be like 0.7. And our nonmetal could be like fluorine, 4.0. So there's a huge difference between those electronegativities. And because that difference is so big, they say generally on average, approximately 1.7. If the electronegativity difference is greater than 1.7, you're going to have an ionic bond. Okay? So if the electronegativity difference between the metal and the nonmetal is 1.7, it's ionic. Now, that's a general statement. There are exceptions to that. In chemistry, there's lots of exceptions. The rule still is, if it's a metal with a nonmetal, it's ionic, no matter what the difference is. Okay? However, for the most part, the difference will be greater than 1.7. Now, covalent bonds. As we know, covalent bonds are the bonds that form in molecular compounds. So these are the bonds that form between what we call non-metal atoms. So if you look at two atoms that are sharing electrons, if they have the same electronegativity. So if I have two hydrogens, here's one hydrogen, here's the other hydrogen. Hydrogen's electronegativity is 2.2. So if two atoms are trying to share these electrons and both of their electronegativities are the same, they will share them equally. Okay, they're pulling on them with the same strength. So the electrons are shared equally between the two atoms, and this makes what we call a nonpolar covalent bond. Okay, the word polar means like there's opposite ends. There's no opposite ends here. The electrons are moving around very symmetrically. So they're going to spend equal time around each hydrogen. So the electron cloud that forms from the sharing of electrons is symmetrical. Okay? I'll show you on the next slide how it can look different when they're not sharing equally, when they don't have the same electronegativity. When they don't have the same electronegativity, this is what it looks like. So if I have fluorine here bonded to hydrogen here, hydrogen is 2.2 and fluorine is 4.0, the electrons are being pulled by the fluorine. So the electron cloud is going to be more dense around the fluorine, and it's going to only spend a little bit of time around the hydrogen. And so that's what makes this lopsided looking bond. And this is called a polar covalent bond. The sharing is no longer equal. The element with the higher electronegativity pulls the electrons closer to itself. So we have a buildup of negative charge here, which leaves us with a buildup of positive charge here. Now, saying this negative and positive charge ends is kind of inaccurate because a negative and a positive end can only form when there's a complete transfer of electrons. So what we say is there is a slight negative charge and a slight positive charge on the two different ends of the bond. Okay, so this is a small Greek symbol delta. So delta negative is the slight negative end, the end with the higher electronegativity, and the slight positive end is the end with the lower electronegativity. Okay, so the electron cloud is lopsided. There's a buildup of electrons on one end compared to the other. This makes, again, what we call a polar covalent bond. So here's a little demonstration. I'm going to go back here for a sec, but what the demonstration is going to show is dogs trying to share bones, just like atoms sharing electrons. So the first one represents metallic bonding. We talked about that in the last lesson. Remember, in metallic bonding, all of the atoms share all of the electrons. So that's what's happening here. All of the dogs, there's 6 of them, they're all sharing all of the bones. And that's just like metallic bonds. The bones or the electrons are delocalized. They're free to move between all of the metal cations. Whereas in an ionic bond, one wins over the other. One then becomes positive, one becomes negative, and they get attracted by their opposite charges. So if we watch that again, the chlorine, the nonmetal, wins, and then the sodium is attracted to the chlorine by their opposite charges. In a covalent bond, they're sharing the electrons. It's nonpolar covalent if they're sharing them equally. If they share them unequally, and we then therefore get, this should really say, a slight positive and a slight negative charge, that is our polar covalent bond. Okay? Here's another image for you of the electron clouds overlapping when they share electrons. So these two elements, again, they're the same element, so obviously they have the same electronegativity. So they share the electrons equally. That electron cloud is symmetrical. Here, my hydrogen is 2.2 and my oxygen is 3.4. So the electrons are being pulled towards the oxygen, making the oxygen build up with a slight negative charge, and the electron cloud being less dense around the hydrogen, so it builds up a slight positive charge. Okay.
Interruption. This is the last call for any junior high students, grade 7, 8, or 9 that need their picture taken to head to the cafeteria. So last call for junior high students, grade 7, 8, or 9. Please head to the cafeteria for your picture if you haven't yet. Thank you.
So as I mentioned, this just explains the polar bond. Okay, so when you have, again, your two atoms pulling on the electrons unequally, so you have to look up the electronegativity of the elements. Hydrogen is 2.2, chlorine is 3.2. So the electrons are going to be pulled, the electron cloud gets pulled towards the chlorine, making the chlorine end have a slight negative end, and the other end being slight positive. So this unequal sharing of electrons is what we call polar covalent bonds. Sometimes they're also called bond dipoles because the bonds have oppositely charged ends. Now you may be asked to draw a bond dipole diagram, sometimes also called bond dipole arrows. In order to do that, you again figure out the electronegativity of your two atoms that are sharing electrons. Whichever one is higher, the arrow points towards it, and you label it as the slight negative. Whatever end is the lower electronegativity becomes the slight positive end. And we also kind of put a little plus or a little tail on the arrow that looks like a plus sign to show that it's slight positive. Okay. We also sometimes above the arrow can write whether or not the bond is polar, a P for polar, and an NP for nonpolar. So this bond is polar because it's between two nonmetals and they're sharing the electrons unequally because they have different electronegativities. There's some here for you to try drawing the bond dipole diagrams. So you're going to identify, are they polar? You can put a P if they're polar, put an NP if they're nonpolar, and put an I if they're ionic. So again, they're polar if there is a difference in electronegativities. I'm writing a triangle here representing difference. It's nonpolar if the electronegativities are the same. And it's ionic if it's between a metal and a nonmetal. Okay, so pause this video, try drawing the dipole arrows, labeling the positive and negative ends, and stating the bond type. For example, here, I would write my electronegativities. There's no arrow because they're sharing them equally, so I just write nonpolar on top. Whereas here, I do have a difference in electronegativity, so it is polar, and I draw the arrow pointing towards the element with the higher electronegativity, with the positive tail at the other end. I label this end as slight positive, and this end as slight negative. Okay, so pause the video, go through, and see if you can get the correct answer. When you come back, I will put up the answers. Okay, so welcome back. Here are your answers. The first one, like I said, is nonpolar because they have the same electronegativity. The second one is polar. The N is the slight negative and the H is the slight positive. The third one is polar. The B is slight positive and the F is slight negative. The fourth one is also polar. The S is the slight positive, the O is the slight negative. 5 is nonpolar. These are two different elements, but they actually have the same electronegativity. So just because they're different elements doesn't mean they have different electronegativities. You actually have to look them up each time. Okay. Carbon and hydrogen is polar. The carbon is higher, so it has the slight negative, leaving the hydrogen slight positive. 2 chlorines obviously have the same electronegativity, so they're nonpolar. Silicon with chlorine. The chlorine has the higher electronegativity, so the arrow points towards it, leaving the chlorine slight negative and the silicon slight positive. Between oxygen and hydrogen, again, the oxygen has a higher electronegativity, so it arrow points towards the oxygen. and the slight negative is at the oxygen, the slight positive is at the hydrogen. And the last one, again, you do not draw an arrow. The arrows only are drawn if it's polar. It shows an unequal sharing of electrons. That's what the purpose of the arrow is. Okay? Whereas in ionic, there's no sharing. There's a complete positive and a complete negative charge. Not a partial positive and partial negative, but a complete positive and a complete negative. Okay? So you just label it as being ionic. You label its specific ion charges. And again, no arrow. You just say it's ionic. Okay? Now one last thing here before we talk about your assignment today. So I mentioned this already, but again, if the electronegativity difference is generally or mostly above 1.7, it'll be ionic. Okay? However, still, if it's a metal with a nonmetal, it's always ionic. It's just most of the time, the difference in electronegativity between the two atoms is going to be greater than 1.7. If it's between 1.7 and greater than 0, it's polar covalent. And then if it's electronegativity difference of 0 between the two atoms, so in other words, they have the same electronegativity, it's a nonpolar covalent bond. So this is kind of, again, a generalization. It's not always 100% true for the distinction between ionic and molecular, right? Generally or mostly, these are your molecular compounds below 1.7, and above 1.7 are your ionic compounds. However, again, it really just depends. If it's nonmetal with nonmetal, it's molecular. If it's metal with nonmetal, it's ionic. Okay? And then within molecular, you can have a polar covalent bond or a nonpolar covalent bond. They're sharing their electrons equally. Here they're sharing the electrons unequally. We have a slight positive and a slight negative end. Here, there's a complete positive and a complete negative end. Here, there's no distribution of charges. It's all neutral. Okay? So this here is another diagram. Now, some places say that if the electronegativity difference is less than 0.3, it's nonpolar. But for us, it's 0. Okay? If the electronegativity difference is 0, right, the electron cloud is distributed between the two evenly. If it's between 0 and 1.7, it's polar, and it's not an equal distribution. There still is some overlap, but again, they're spending more time around the element with a higher electronegativity. So there's a buildup of negative charge there. It's slight negative charge, and the other end is slight positive. And last is ionic. The electron clouds are two separate clouds now. There's no overlap at all. And there's a complete positive and complete negative charge. Okay? So, like I was mentioning at the end here, that continuum, if I go back here, we're referring to this continuum. This continuum is, there's no discrete cutoff. That 1.7 is not always 100% true. Okay? So that's all these last couple of sentences are saying. Now, what you need to do in your assignments, there's actually a couple of assignments. One of the assignments is in your textbook on page 41, question number 10 to 12. You're going to draw bond dipole diagrams for those. And then the other part of your assignment is in your workbook, column 1 to 4, sorry, page 1 to 4, column 5. And what you're doing is you're going to look at your molecules and identify if the bonds within your molecule are polar or polar or nonpolar. Okay, so for example, CH4. This is what your structural diagram for CH4 looks like. You're just looking at the individual bonds. So my bond is from C to H. There's 4 of them, but that's what the bond is. Is that bond, or are those bonds polar or not? So if they have electronegativity differences, carbon is 2.6, hydrogen is 2.2, so they do, therefore the bonds are polar. You are going to get some where you have, for example, bonds that are both polar and nonpolar within your molecule. So my C to C bonds here They both have the same electronegativity. Sorry, they should be 2.6. They both have the same electronegativity. So the bonds between the C are nonpolar, but the bond from the C to the H's, because the H's are 2.2, are polar. So you're going to say that then they have both polar and nonpolar bonds within the molecule. Okay, so you're looking at the bonds within the molecule. Are the bonds polar, nonpolar, or both? Okay, those are your three options. This would be nonpolar. This bond here is nonpolar because they're the same element, same electronegativity. This bond would be polar because they have different electronegativities. And this molecule has both polar and nonpolar bonds. The C to C bonds are nonpolar and the C to H bonds are polar. You don't have to identify which is which. You don't have to draw anything. The only thing you need to do for column 5 is put P for polar, NP for nonpolar, or both for both. Okay, check the answer key as you're working. Make sure you're getting the correct answer. And if you have any questions, feel free to email me. Thank you.